In this video, I'm going to talk about linear transformations, which are transformations that can help a lot with the interpretation of the coefficients. The transformation we're going to talk about are centering, scaling, and standardizing. So what is a linear transformation? Well, it's when we take our variable and we either multiply by a constant, or add a constant, or both multiply it by a constant and then add another constant. This transformation could be applied both to x variables, the explanatory variables, and y variables, the dependent variables. They are very useful because they can ease the interpretation for our estimated coefficients. For instance, they can align the definition of slope coefficients with common units. Or for instance, you have one unit for x in centimeters, and the other unit is feet or yards or any other ridiculous unit system. It can also provide an intuitive definition for the intercept. For instance, if you switch the temperature from Fahrenheit to Celsius, then now x equals 0 is interpretable. It's the freezing point for water. And finally, it could ease the interpretation when the audience is less familiar with a variable or unit, which is my case for any imperial units. You would have to switch it to metric for it to make sense to me. They impact only the estimates for the intercept and slopes. They will not affect the r-squared or the p-values from our regression. The first transformation that's very common is called centering. It's when a value is just added or subtracted from one or more of the variables. It only impacts the intercept, so the slope coefficient will not change. It's useful to ground the intercept in our data and give it meaning. So now, when we have changed x to x nu by adding or subtracting some variable, hopefully when x nu equals 0, then the y hat is equal to alpha hat, and this has some meaning that it didn't have before. For instance, when we subtract the minimum value of the variable x, now the intercept is interpretable because x nu equals 0 is both realistic, it happened, it's the minimum value in our dataset, and it is in the range of our data. The other case is when we subtract the mean value of the variable, that's called mean centering. In that case, the intercept is the expected value of y for the average x. So we could think of it as a representative x. The next transformation is called scaling. It is just multiplying or dividing a variable by some value. For instance, the new x is the old x times b. It is commonly used to have similar units in both x and y. For instance, you have a dataset where y is in millions of dollars and x is just in dollars. So to facilitate the interpretation, you will create a new x which is also in millions of dollars. This only impacts the slope coefficient. For instance, if you have y in millions of dollars, for the x old you find that the beta coefficient is 0.00000023. It's hard to interpret. However, if you change x to be also in millions of dollars, then the coefficient beta becomes 2.3, which is a lot easier to interpret. Now we have a sense of the scale. An increase in x by $1 million is associated with an increase in y by $2.3 million on average, and everything else being equal. Finally, let's cover the standardizing transformation, which is probably the most common one in some fields. When we standardize a variable, we subtract the mean of this variable and we divide by the standard deviation. So now we have a new variable with a standard deviation of 1, so a variance of 1, and a mean of 0, which is very convenient. It helps people who read the result to infer the practical significance when they may not have a sense of what's the original distribution. Because now the interpretation is in standard deviation. This transformation impacts both the intercept and the slope. Here is an example of interpretation. Let's say we find an estimated coefficient of 0.2, then the interpretation would be, on average, an increase in our new x by 1 standard deviation is associated with an increase in y by 0.2 standard deviation, everything else being equal.